morning. Today we're going to do Unit 10, Classwork 2, Properties of Tangents. So for our prior knowledge question, it says, name the term that best describes the notation. Over here, F. You got to look over here. Oh, here's F. Recall F is that point of tangency. It's where the tangent point meets the radius to create that 90-degree angle. FE, here's FE. Oh, got the tangent. GH, the segment GH, radius. D to B, notice the notation above DB. It could be a chord or it could be a secant, and I'm going to call this one chord. Point C is the center. Segment BE. It's a chord, but a better name for this chord is the diameter. Line DB, that's your secant. And line AG, that's your tangent. Okay, properties of tangents. We went over these last time. We're going to review them today. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So here it says PQ is tangent to circle C at P. And if it's tangent, we know that that's a right angle. If PQ equals 5 and CQ equals 6, all of CQ equals 6, then find CP and find the measure of angle C. So in order to find CP, let's put an X here. Pythagorean theorem. X equals square root. Since we're looking for a leg, it's going to be 6 squared minus 5 squared. So that is square root 11. So CP equals the square root of 11, or CP, if you rounded it, is approximately 3.32. Now we need to find the measure of angle C. Let's go ahead and put a theta here. All right, so recall SOHCAHTOA. If I want to find a missing angle, I set up the regular ratio and then do the second button on my calculator, right? We want the inverse. So it looks like if I put my finger on C and point to the opposite side, and I was given the hypotenuse, opposite over hypotenuse is sine. So we're going to go sine of theta is 5 over 6, which means theta equals the inverse sine 5 over 6, which means the measure of angle C, 56.44 degrees. So knowing that it creates a right angle, we could ask you whether a line segment is tangent or not. And how do you verify this? Well, again, I'm given 3 sides of a triangle, and if that's a right triangle, then that angle T, the point of tangency, would be a right angle. So what we're looking for is that a right angle? So here we go. We want to know is 12 squared plus 35 squared equal to 37 squared. Sometimes it's confusing the way the diagrams are drawn, but remember, the hypotenuse is always the longest side. So your right angle is always going to be across from that longest side. So here we go. We have 144. 12 times 12 is 144. 35 squared is 1, 2, 2, 5. And 37 squared is 1, 3, 6, 9. When I add those together, 1, 3, 6, 9 equals 1, 3, 6, 9. Those are a match, which means Pythagorean theorem proves that ST is tangent to circle P. All right, and then this is our tricky one. You're going to see this problem a lot, so I'm going to keep putting it on. We want to know what the radius is. And so from A to C, this whole length is 50 plus R. So when we say R squared plus 80 squared equals 50 plus R squared, that 50 plus R times 50 plus R is going to equal 55 times 50. 5 times 5 is 25. 2500 plus 100R, 50R plus 50R plus R squared. So we're going to rewrite it over here. 80 squared, 8 times 8 is 64. So we're going to have R squared plus 6400 equals 2500 plus 100R plus R squared. And notice, in these problems, the R squareds cancel out. So 6400 equals 2500 plus 100R. We're going to subtract 2500 from both sides, and we're going to get 3900 equals 100R. Divide by 100. R equals 39. The other theorem about tangents: if two segments from the same exterior point are tangent to a circle, then they are congruent. So given that AOC and, or given that OA and OC are radii, that's what we're given. OA and OC are radii. Radii is plural for radius. And AB and CD are tangent segments. Use the hypotenuse leg shortcut to prove that AB is congruent to CB. So we're going to prove this theorem using stuff we already know. So OA and OC are radii. What do you know about radii? They're all the same length. That's the definition of what a radii is. And we were also given that AB and CB are tangent segments. So that was given to us. And if they are tangent, lines are perpendicular. And so if lines are perpendicular, we've got an angle that measures 90 degrees. So we know that BAO and BCO both equal 90 degrees because that's definition of tangent. BO is congruent to BO. Reflexive property. And so, triangle BAO is congruent to triangle BCO. Hypotenuse leg. Well, they already gave that to us. And therefore, AB is congruent to CB, P, T. How did I keep track of all of that? Well, what we forgot to do is mark our diagram. So let's go up and mark our diagram. Mark. Okay, I want to mark A and C. We were given that. We also know that the radii are congruent. Let's get a different page. We knew that the radii were congruent. And then we use the reflexive property. So there you can see the hypotenuse leg. What we were proving was AB congruent to CB. So now that we've done the triangle proof, we know in fact that the rest of the congruent parts must be congruent. So AB must be congruent. Our next question is, what angles would you say are also congruent by CPC-TC? These two up here and these two down here. They must be congruent by CPC-TC. So angles ABO congruent to CBO and BOA COB. BOA BOC. What kind of quadrilateral is ABCO and how do we know? Well, I know. Kite. And I know it's a kite because we've got two distinct pairs of congruent adjacent yep. Just going to write consecutive sides. Dyslexia is getting me. So now that we know that there's a kite inside when we have tangents, and we've proven that those, if there's an exterior point that's tangent, that has two segments tangent to the circle, that those segments are congruent, you can go ahead and solve these problems now. So RS is tangent to circle C at S, RT is tangent to circle C at T, find the value of its exterior point. These two segments are congruent. It's a kite. The radii are always congruent. So we can say 3x plus 4 equals 28. Subtract 4 from both sides. 3x equals 24. And then the last thing about tangents that we know is that a circumscribed polygon is a polygon in which each side is tangent to a circle. And so we're going to use this previous statement that says if two segments from the same exterior point are tangent to a circle, then they are congruent. We're going to use that here. I know that those two segments must be congruent. I know that these two segments must be congruent. I'm going to do 3 ticks up here. And I'm going to do 1 tick here. And I know that those segments must be congruent. Here we go. If MK is 7, then KN is 7. If JO is 12, MJ is 12. And then I got this nonsense. 4x minus 9 equals x plus 3. Let's go ahead and set those to equal and see what x equals. I'm going to say 4x minus 9 equals x plus 3. Subtract x from both sides. I've got 3x. Add 9 to both sides equals 12. Means x equals 4. Plugging 4 in. 4 plus 3. 7. 4 times 4 is 16 minus 9 is 7. So if we are going to find x, which we did, and then find the perimeter, we have 2 12 plus 4 7. The perimeter is 24 plus 28, which means our perimeter is 54.